Hello everyone, in this video I am going to talk about a paper which is titled Next Generation Reservoir Computing. My name is Randy Cahyawihandika and the paper is written by Daniel Gauthier and other co-authors in 2021, and this video is an assignment of the time series analysis course. And since this topic may be new for some people, so I would like to start with the basic of artificial neural networks. And then we will move on to the traditional reservoir computing, or RC. And then finally, we will discuss about the next generation reservoir computing, or NGRC. So in artificial neural networks, it is inspired by biological neuron cells that we have in our brain. Like we have right here, this entire cell is an example of a neuron cells. And there are some parts of it. Here we have the nucleus, or the core of the cell, and we have the dendrites right here, which accepts signals from outside, and we have axons right here that transmit the signals to the other end of the cell. Then in artificial neural networks, we have also the core of the cell, or like the nucleus, and we also have the dendrites here, which accepts the input signals, and the input signals right here will be combined, which is usually using linear function, and the result of this linear function will be transformed by an activation function, and the result of this activation function is the output of this entire artificial neuron cells. And in artificial neural networks, we have a lot of cells, like we talked about in the previous slide, and the cells are connected to each other, creating a neural network. So signals are transmitted from one neuron to the other. So for example, here, this neuron accepts signals from other cells and processes it, and then transmit to other neuron cells. So in a neural network, there are many neuron cells that work together as a network. There are many types or architectures of neural networks, and one of the most popular is the feed-forward neural networks, where the neurons are arranged in layers. So here we have the input layer, or layer number 1, and layer number 2, 3, 4, and so on. And a neuron is connected to other neurons in the next layer, like we see in this picture. And usually in this picture, the data flow is coming from the left side to the right hand side. And one characteristic of this architecture is that it works with the input and output of fixed length. So we have a certain number of input layer and also a certain number of output layer right here. Another architecture of a neural network is the recurrent neural networks, or RNN, where in this architecture, neurons can have a connection to itself, and it works with the input of variable length. So it doesn't have to be a certain length. The length of the input and also the output can be any length. So the input can be in the form of sequence, for example, text, and other time series data. And in reservoir computing, it is an improvement over the echo state networks, or ESN, and liquid state machines, or LSM. And it is based on the recurrent neural networks, or RNN, that we talked about in the previous slide. And in reservoir computing, or RC, there is a pool of interconnected neurons that we see right here in this circle. It contains many neurons that is connected to each other, or we can say it is a pool or a collection of RNNs that will process time series input, and they will give an output right here. And the cells right here also have an activation function like we have in feed-forward neural networks. And here we see the differences between the feed-forward neural networks, or FNN, versus the RNN versus the reservoir computing, or RC. We see here in the FNN, everything is in blue line. So we have these lines or connections from the input to the neuron cells and to the output, and they are all blue, meaning that they are trained connection that will be trained in the training phase. And in RNN, it's almost the same. Every connections in blue line, except that the connection can be made from one cell to itself. And in RC, we see that the color is different. It is in black color, meaning that it is fixed connection. It means that in the training phase, we don't train this connection right here. Uh, we, we will only train this connection right here. So in RC, the input layer and reservoir weights are assigned randomly right here and kept fixed, not trained. And only the output layer weights are trained right here. And the readout function of the reservoir is most commonly a single fully connected layer that is right here. And it is also possible to use more sophisticated functions like the support vector machines, or SVM. And there are a number of advantages of the reservoir computing. First one is it is versatile, meaning that it can be used for any temporal input-output task. And the reservoir itself does not need to be modified or trained, like we discussed in the previous slide. And the training procedure is straightforward and fast and can be performed through only a simple linear regression. So it's very fast. It requires substantially smaller training data than deep learning methods that we know. It is hungry for data. And a single reservoir can be used to learn multiple different tasks, and it is extensible. There are many additions to the basic RC that have been proposed in many researches. In standard RC, like I have mentioned in the previous slide, the reservoir is kept fixed and only the readout map is trained. It may also be beneficial to also optimize the reservoir itself right here to increase the system's performance. And the tuning can be done either manually or automatically using grid search, random search, or evolutionary search. So we can get the best of the reservoir that we can use in our system. A reservoir computing aims to broadcast input data that we call X here into the higher dimensional reservoir right here. So here we have the input data. And the reservoir is it's composed of n interconnected nodes right here. And the RC then combines the resulting reservoir state into an output that we call Y that closely matches the desired output that we call YD. And the strength of the node-to-node connections in the reservoir right here is represented by the adjacency matrix that we call A, that is chosen randomly and kept fixed. It means that it is not trained. And then the input data X is broadcast into the reservoir here through the input layer with a fixed random coefficient W. So we have here two matrices, the A and W, which values are chosen randomly. Then we look a little bit deeper to the reservoir computing. The reservoir is a dynamic system whose dynamics can be represented by the formula right here. We see here we are calculating the R at I plus 1, where I is the time step, equals, there are two terms here, two parts. We can see here that we are calculating the R at I plus 1 that we calculate based on the R at time step I. So we are calculating the reservoir state at the next time step. And in this part right here, we can see that we are maintaining the reservoir state at the previous time step that we maintain at some extent, which is specified by this gamma, or the decay rate of the nodes. And then we combine it with the second part right here that we calculate with the decay rate multiplied by the f, or the activation function. And this part right here that we get from the adjacency matrix, the previous reservoir state, the matrix W, and the input plus the B, where B is a bias vector. And for simplicity, the value of gamma and B, or bias, can be given the same value for all nodes in the reservoir. And the author mentioned that the random matrices, there are two matrices, the A and W matrices, can cause problems because not all matrices work well because it's random. There is little guidance to select bad or good ones. And there are several metaparameters that can greatly affect the performance and require optimization. And these problems are solved in the NGRC, which the author also called the nonlinear vector autoregression, or the NVAR. So in a standard or traditional RC, the activation function in the reservoir is nonlinear here, and the feature vector in the output layer is linear. And in different approach, the nonlinearity is swapped. That is, the activation function in the reservoir is linear, and the feature vector in the output layer is nonlinear. So that's a different approach to the standard reservoir computing. And the nonlinearity is achieved by squaring the values of all nodes through the Hadamard product. Here, it is symbolized by this symbol right here. So the feature vector in the standard RC is given by the O total equals R. This operator is the vector concatenation operation that is concatenated with the result of the Hadamard product. And such configuration shows comparable performance to the standard RC. While in NGRC, the feature vector, or O total, is given by C concatenated by the O linear concatenated by the O nonlinear. So there are three parts right here. C is a constant, and O linear is explained here in the next point. And the O nonlinear is the nonlinear function of O linear. And the O linear part is given by this. So it's the xi, the input, concatenated by the x I minus s, and so on, xi minus 2s, and so on, until xi minus k minus 1s, where s is the spacing between the consecutive observations, and k is the number of observation. And we can see right here in this NGRC compared to the standard RC, this formula that we have above does not involve A, W, bias, and etc. that we have in the standard RC. It means that this NGRC lacks of a reservoir, or it doesn't have a reservoir. So it is a little bit ironic. We here have an NGRC reservoir computing, but it doesn't have a reservoir. Here we see the traditional RC from the input vector or input data. We broadcast it to the reservoir, and then we calculate the reservoir state R. And then finally, we will get the final output, the Y right here, with the same formula that we have discussed before. And while in the NGRC, from the input, we directly calculate the O linear vector and then the O nonlinear vector, and then we form the feature vector, the O total, and then we can calculate the final output, the y right here, without involving the matrices W, A, the bias, and so forth. And this configuration has been proven mathematically to be uh, equivalent. So the RC, the traditional RC, is equivalent to the NVAR, and this NVAR is what the author called the NGRC. So this is equivalent with several additional advantages. And then the output with matrix W out is obtained by learning using least squares. So using this formula, we calculate using the O total, which is the feature vector that we have discussed before. And we can calculate the W out, which is a matrix, where alpha is the regularization parameter, YD is the desired output, and I is the identity matrix. And after we obtain this W output matrix, then we can get the output layer, which is the final output of the RC, the yi plus 1. We calculate it using the W out and the O total again, and we can get the final output of the reservoir computing. NGRC brings several advantages over the traditional RC. The first one is it uses exceedingly small data sets, and the feature vector is much smaller, so that it requires dramatically shorter warm-up period, and it resolves the random and parametric difficulties in traditional RC. We have discussed that in traditional RC, we use the matrices W, A, and also the parameter, the alpha, and so forth. And it has fewer meta-parameters to optimize so that it will be more computationally efficient. Then for the experiments, the author performed 3 experiments. The first one uses the Lorentz 63 weather system for one-step ahead prediction, and the training data consists of only 400 points, and the training time is very short. It is less than 10 milliseconds on a standard single-core processor, and the result is comparable to an optimized traditional RC with 100 to 1000 of reservoir nodes or neurons. And the performance is measured in terms of normalized root mean square error, which is 2.4 plus minus 0.53 by 10 to the power of minus 3. And that is quite a very small number for an error of a system. And this is the visualization of the first experiment. So this butterfly-like shape is the ground truth data, and the red one right here is the prediction by the NGRC. And these graphs right here is the training data, and this part right here is the prediction result, where the red curve is the prediction and the blue curve is the ground truth. And here we can see almost, although it's not perfect, the prediction is quite successful in following the pattern of the general data right there. The second experiment uses the double scroll electronic circuit for one-step ahead prediction, and the result is measured in terms of the NRMSE, and the result is 4.5 plus minus 1 by 10 to the power of minus 3, and is also very small. And for the second experiment, uh, this is the result, where this is the ground truth and the prediction, and this is the training data, and this one right here is the prediction result. And here we can see that the NGRC is successful in obtaining the pattern of the data. For the last experiment, it uses all 3 Lorentz 63 variables. So there are 3 variables during training for next step ahead prediction. And the training data consists of only 400 points. and it infers the z variable from the x and y variables during testing. So the x and y variable is used in the training, and it infers the z variable. And the result is 1.5 plus minus 0.3 by 10 to the power of minus 2, and that's also quite small. Here we see the result of the last experiment. On the left side, we see the training data, and on the right side, we see the testing data. And there are three variables, x, y, and z. And we can see on the figure C here, although we only see a red curve, actually because the performance is so good, we don't see any difference, where actually there are two curves right here, red curves and blue curves. Blue is the ground truth and the red is the prediction curve. And because the performance is so good, we cannot see any difference. It also happens in the graph right here. Actually, there are two curves right here, and because the performance is very good, we don't see any difference here because the result is identical between the prediction and the ground truth. And to conclude, this is a summary. RC is a technique that is well suited for learning dynamical systems, even when the system shows chaotic or complex data, such as the data that has been tested in the experiment. And GRC is an improvement over the traditional RC that has an underlying implicit or hidden traditional RC. So even though we do not see the matrices A, W, and etc., there is an hidden RC inside the NGRC. NGRC can perform well in cases where traditional RC can be applied and may perform even better. NGRC requires less training data, has fewer metaparameters, thus needs less computational power or resources compared to the traditional RC. So that's it for the discussion about a novel method called Next Generation Reservoir Computing, or NGRC. Thank you for watching.